Hello students, welcome to MEMONEET. I am Prachita, your chemistry tutor. How are you all doing? So I hope everyone is doing good and the preparation is going well as well. So today we are going to continue our chapter coordination compounds. In the last video lecture we have studied about the valence bond theory. I hope valence bond theory is clear to everyone. But we discussed that valence bond theory had certain limitations. So then we will be now studying the crystal field theory. Okay, so from valence bond theory, we get to know about the structure, the shape, and the magnetic nature of the coordination compounds, but we don't get any idea about it is based on assumptions. We don't know about the weak ligands, strong ligands. Okay, it's just the assumption. Moreover, it does not tell us about the stability of the coordination compounds. Okay, so then there is another theory which we call as crystal field theory that we will be covering today, and then we will be seeing some of the applications of coordination compound. Then our chapter would be complete. Okay, so stay till the end because in Neet exam questions are asked from the application part also, so don't skip that application part as well. All right. So we will be starting with crystal field theory. Now what is this crystal field theory? It is actually an electrostatic model. Okay. So we have, what do we have in our coordination compounds? We have metal and the ligand, right? So metal and ligand bond, it considers the metal and ligand bond to be ionic. Okay. So this theory says that the metal and ligand bond is ionic and there are electrostatic interactions between the metal and ligand. So ligand are treated as the point charges. Okay, it treats the ligand and the point charges, and point in case of anions, if we are having anionic ligand, so it will consider them as point charges. If we have dipoles, if we have neutral molecules, it will consider them as point dipoles. Okay, see now if I talk about the d orbitals, okay, because we have seen कि in transition elements are involved in this coordination compounds, and the empty d orbitals are the ones that participate in the bonding. So you know that there are 5 d orbitals. Okay, we have studied about the orbitals already. So 5 d orbitals in any isolated gaseous metal atom have same energy. तो वो पांचों जो d orbitals होते हैं उनकी एनर्जी सेम रहेगी. ओके, so there are dxy, dyz, dzx, dx square minus y square and dz square. These are the 5d orbitals. So ये जो तीन होते हैं, they are in between the axis. जैसे अगर मैं बात करूँ x y z की, so if this is x and if this is y, so this will be your dxy. Okay, ऐसे dyz and dzx, but dx square minus y square is like this. Okay, they are along the axis. So ये आपको पता होना चाहिए. And dz square is also along the axis. So ये इसकी shape होती है and then it has this thing, right? So that we have already studied, but they are degenerate. Degenerate का मतलब पता होना चाहिए. Degenerate means they will be having same energy. Okay. So this degeneracy is maintained if a spherically symmetric field of negative charges surrounds the metal atom. Okay, अगर spherically symmetric होगा तो degeneracy maintained रहेगी, मतलब energy same रहेगी. But when the ligands approach the metal ion, okay, when this negative field is due to ligands. अब ligands can be anions also or negative ends of the dipoles as well. Okay. So yeah, if I talk about these d orbitals, these are degenerate, but we were saying कि when our ligand approaches the metal ion, it can be an ionic ligand or the negative dipolar end of the molecules like ammonia and water. So it becomes asymmetrical, okay? And when it becomes asymmetrical, the degeneracy is lifted and it results in the splitting of d orbitals, okay? So the splitting takes place in such a way that these three orbitals, which are like pointed or oriented, I can say, along the between the axis, so they are see, they have written here, they are oriented in between the coordinate axis like this. Okay, so these three will be splitted alone and the other two will go other way. Okay, so these orbitals which are oriented in between the coordinate axes are called T2G orbital. Now the meaning of this T2G you will be learning in higher classes, okay? It depends on symmetry and all of that, but try to understand they are called T2G orbitals. And dx square minus y square and dz square, they are oriented along the x and y axis, okay? So they are called the EG orbitals, okay? So due to when the ligand approaches, these 5 degenerate d orbitals split, and this splitting depends on the nature of crystal field, okay? Now, the energy difference between these T2G and EG levels is designated by delta. Okay, this is delta, and we will be calling it as crystal field splitting energy. Alright, so we'll be calling it as crystal field splitting energy, and let's move ahead. So this crystal field splitting energy and this all will depend on the type of ligand that we are having. In the last lecture I talked about this thing, your weak field and strong field ligand. So this data has been experimentally determined. Okay, the spectroscopic data has been experimentally determined by taking like all the experiments were done, and we get the spectrochemical series. Okay, so this is your spectrochemical series, you have to remember it. So see, this is water. After water, usually the ligands are considered as strong field ligands, and below water, these are considered as weak field ligand. Okay, so they are arranged in increasing order of magnitude of crystal field splitting. So basically what is happening, let's say if I am having chloride ligand and I am having ammonia ligand, so ammonia will cause larger splitting. Okay, so there will be more energy difference, delta would be more, crystal field splitting energy would be more in the case of ammonia rather than chloride. So that is what crystal field splitting means. Okay, and that depends on the magnitude or the strength of the ligand. Okay, so remember this series as well, this is important. So now we have discussed two type of complexes, octahedral and tetrahedral. So we'll be discussing both of them. Now in octahedral this complex, we have 6 ligands which surround the metal atom. Okay, and there will be repulsion between the electrons in the metal d orbitals and the electrons of the ligand. Negative negative repulsion hoga, like when ligand approach, so electrons are present in the d orbital and the electrons are present in the ligand also, so there will be electron repulsion. Okay, repulsion will be more when metal d orbital is directed towards the ligand than when it is away from the ligand. तो octahedral complex में क्या होता है, let's say if I am having this, so जो ligand है वो along the axis approach करता है, right? The ligand approaches along the axis. अब along the axis कौन से orbitals present होते हैं, dx square minus y square and dz square, right? ये दो orbitals present होते हैं, these point towards the axis. तो अब ये दो जो हैं, they will experience more repulsion क्योंकि इनकमिंग ligand is also in the same direction. बाकी के जो ऑर्बिटल्स हैं, they are between the axis, so they will experience repulsion, but उतना नहीं, okay, कम. So the dx square minus y square and dz square orbitals, they are pointed towards the axis and they will experience more repulsion. Okay, and they will be raised in energy. And dxy, dyz, dzx, which are directed between the axis, will be lowered in energy. तो जो relative average energy रहेगी उस crystal field की, तो उससे भी low energy पर वो चले जाएंगे. Okay, so degeneracy has been removed now due to ligand electron and metal electron repulsion. Okay, so we have got 3 orbitals of lower energy T2G and 2 orbitals of higher energy EG. Okay, so this is known as crystal field splitting and energy. अब octahedral की बात कर रहे हैं, so the energy will be denoted like this, delta naught. Okay, O stands for octahedral. Okay, and this has been experimentally determined. So let's see the diagram here. Can you see here, students, that this is the energy diagram? So these are the metal d orbitals, 5 d orbitals are there. So average energy increases in terms of like in spherical crystal field. So this is the average energy. So average energy से क्या होगा, in the presence of ligand in octahedral crystal field, the energy of dx square and dz, dx square minus y square and dz square orbital will increase by 3 by 5 delta naught. This is important. And the energy of dxy, dyz and dzx orbital will decrease by 2 by 5 delta naught. So ये diagram आपको याद रखना है. So now the electrons are filled accordingly. Okay, अब electrons कैसे fill होते हैं? Okay, so this whole is delta naught, right? This difference is the delta naught. So we will be comparing delta naught and P. Now what is this P? P is the pairing energy. Okay, P is the pairing energy. अब देखो, if delta naught is less than P, अगर pairing energy ज़्यादा है, so let's say how the electrons are filled. Let me show you. Okay, so you know we will be like applying Hund's rule, Pauli's exclusion and all of that. So एक electron fill किया, 2 and 3. So 3 electrons are filled like this. D orbital की हम बात कर रहे हैं. Now अब 4th electron कहाँ जा सकता है? वो ऊपर भी जा सकता है और वो पेयर भी हो सकता है. अब वो क्या दो केस रहेंगे? If pairing energy is more than delta naught. Okay, अब pairing energy जो है वो ज्यादा है एंड डेल्टा नॉट कम है, तो इलेक्ट्रॉन क्या करेगा? इस डेल्टा नॉट को इजीली ओवरकम करके ऊपर ईजी ऑर्बिटल्स में चला जाएगा. ओके, दीज आर ईजी, दीज आर T2G. ओके, सो द फोर्थ इलेक्ट्रॉन विल गो टू द ईजी ऑर्बिटल. सो इसकी कॉन्फ़िगरेशन हम लिखते हैं T2G3 EG1. क्योंकि पेयरिंग एनर्जी ज्यादा है तो पेयरिंग नहीं हो पाएगी. यहाँ पर डेल्टा नॉट की वैल्यू कम है तो इलेक्ट्रॉन जो है वो ईजी ऑर्बिटल में चला जाएगा. एंड द लिगेंड्स फॉर विच डेल्टा नॉट इज लेस देन पी. अभी हमने देखा कि वीक फील्ड लिगेंड्स होंगे तो कम स्प्लिटिंग होगी. सो डेल्टा नॉट इज लेस फॉर द वीक फील्ड लिगेंड्स. तो in this case weak field ligands will form such complexes. Okay, and they form high spin complexes. ये हमने last theory में भी पढ़ा था, but there was no explanation for it. Now we have got this explanation कि why weak field ligands form high spin complexes. क्योंकि electron has gone here, यहाँ पर pairing नहीं हुई है, तो they will form high spin complexes. Okay, now next case you will easily understand. Okay, now let me erase this first. Now if I am talking about the second case, in second case students, if delta naught is more than P, अब डेल्टा नॉट जो है वो बहुत ज्यादा है तो इलेक्ट्रॉन इतनी एनर्जी को ओवरकम नहीं कर पाएगा और ईजी ऑर्बिटल में नहीं जा पाएगा. पेयरिंग एनर्जी कम है सो इट विल प्रेफर टू पेयर अप. तो फोर्थ इलेक्ट्रॉन जो है वो यहीं पर पेयर हो जाएगा. सो द कॉन्फ़िगरेशन विल बी T2G4. मतलब 4 इलेक्ट्रॉन्स आर देयर इन T2G एंड EG में 0. Okay, so P, I told you it's the energy required for electron pairing in the orbital. So strong field ligands अगर होंगे तो ज़्यादा splitting होगी, delta naught will be more and this case will happen and they will form low spin. तो of course this will be a low spin complex क्योंकि यहाँ पर 2 electrons जो हैं वो paired हैं, right? It will be a low spin complex. So this is how electrons are filled according to the crystal field theory. That depends on the pairing energy also. Okay. So how low spin and high spin complexes are formed? I hope this is clear to everyone. So this was for octahedral field. Now let us talk about the tetrahedral field. Okay. Tetrahedral complexes में the d orbital splitting is inverted. अब invert क्यों हो जाती है? Because the ligand approaches between the axes. Okay. अब पहले along the axis ligand approach कर रहे थे. Here the ligand will approach between the axis. So अब क्या होगा? The repulsion for dxy, dyz, dzx will be more. It will go up in energy and the other two will come lower in energy. Okay, and try to keep that in mind कि जो splitting होगी that will also be less. Okay, it is less than the octahedral field splitting. So there is a relation delta T. Okay, delta T means for the tetrahedral complex it is 4 by 9 delta naught. So delta T is less than delta naught. So pairing crystal field splitting for tetrahedral complex is less than crystal field splitting for octahedral complex. And in this case, you can see ki Eg orbitals have lower energy than T2G orbitals. So this thing, they are lowered in energy by 3 by 5 delta T, and here the T2G orbitals go up by 2 by 5 delta T. That is like same. Okay, keep that in mind. And one more thing, try to understand ki delta T is less than delta naught. Okay, so the splitting energies, they are not sufficiently large, okay, for forcing pairing. अब यहाँ पर डेल्टा टी इतना कम रहेगा कि इलेक्ट्रॉन पेयर नहीं होगा एंड इलेक्ट्रॉन विल इजीली जंप टू द upper orbitals, okay, like to the T2G orbitals. So that is why low spin configurations are rarely observed. So usually जो tetrahedral complexes होते हैं, they are high spin complexes, क्योंकि electrons will jump to the T2G orbital, and it is because of less crystal field splitting energy, okay, that is less delta T. And try to understand कि ये जो हम G use कर रहे हैं, T2G and EG, their G stands for G-rad. G-rad and un-G-rad you will learn in higher classes, but see, it is used for the complexes which have center of symmetry. So you know octahedral and square planar complexes have center of symmetry, but tetrahedral complexes, they do not have symmetry. You know tetrahedral complexes are like this, so they don't have any symmetry. So in that case, we will just use E and T2. We will not write G. Okay, subscript G is not used with the energy levels. So in your syllabus, we just have for octahedral and tetrahedral. Otherwise, we in higher class when you will go, you will study it for your square planar and other complexes as well. But right now, this much is enough. Okay. Now let's talk about color in coordination compound. So see, this thing also valence bond theory could not explain. So color in coordination compounds can be explained in terms of crystal field theory. Okay, for example, if I am taking this compound titanium H2O6 3 plus, which is violet in color. Okay, so this is an octahedral complex. Here titanium is in 3 plus state. 3 plus state is 3D1 system. Okay, so 3D1 is like this. So octahedral hai, so T2GeG. So electron is in ground state. Okay, but what happens is when energy is supplied, so आपको पता है कि color is why, because the complexes, they absorb certain amount of light, okay, and uska corresponding color they emit. Okay, so what happens is the next higher state is available, that is the empty EG level. So if light corresponding to the energy of blue green region is absorbed by the complex, कि इतना इलेक्ट्रॉन जो है यहाँ से जंप कर पाए उस फ्रीक्वेंसी की लाइट वो absorb करेगा, and it will jump to the higher energy level. You can see here that it has now jumped to the EG level. Okay, so that is how, अब उसने वो लाइट absorb कर ली, उस wavelength की लाइट, उसका जो corresponding wavelength होगा, that will be emitted by it. Okay, so basically क्या हो रहा है, D ऑर्बिटल में ही ट्रांजिशन हो रही है, राइट, द ट्रांजिशंस आर टेकिंग प्लेस इन डी ऑर्बिटल्स ओनली. ये भी डी थे और यहाँ पे भी डी से, तो डी से डी में ही जा रहा है, सो वी कॉल देम एज डी डी ट्रांजिशंस, dd transition of the electron. So color is because of the dd transition. So you will study it in जब हम D block पढ़ेंगे, in that we will also study कि transition metal complexes are usually colored. Why they are colored? Because of dd transitions, कि electron jump from d orbital to another d orbital only. It absorbs certain amount of energy and corresponding energy it emits. Okay, so that will be like appear in the form of color. Fine. So dd transitions, if someone asks you what is the reason for color in coordination compounds, the main reason is the dd transitions. Okay, so keep that in mind. Next, students, again there are certain limitations of crystal field theory. Although it is successful in explaining formation, structure, color, magnetic properties to a large extent, so like, however, from the assumptions that ligands are point charges, it follows an ionic ligand should exert the greatest splitting effect. But हमने क्या देखा, अब क्या है कि basically we saw, just let me show you the spectrochemical series again. So they are saying कि ligands are point charges and electron repulsion होती है. तो इसका मतलब जो anionic ligands है, the ones that are carrying negative charge, उसमें तो number of electrons ज़्यादा है, so the repulsion should be more and the splitting should be more. But here we can see कि the anionic ligands are at the lower end of the spectrochemical series and neutral ligands जो है generally वो higher end पे है, right? So this theory could not explain this thing कि why anionic ligands are at the lower end of the spectrochemical series. Okay. And it does not take into account the covalent character of bonding. So they are just taking it to be purely electrostatic, electron and electron repulsion hota hai and then splitting takes place. But there are covalent like character bhi hoga usme, of course it's a coordinate bond. So these are some weakness of crystal field theory which are explained by ligand field theory and molecular orbital theory that we'll be learning in your higher classes, not now. Okay. So this is the thing. Now let's go to metal carbonyls. So metal carbonyls are another type of compounds that we will be studying here. Okay. Homoleptic carbonyls का क्या मतलब है? That contain only carbonyl ligands like tetracarbonyl nickel. Okay. NiCO4. Here we have FeCO5. So they are all having carbonyl ligands. Okay, so they have well defined structure. You can see tetracarbonyl nickel is tetrahedral, pentacarbonyl iron is trigonal bipyramidal, hexacarbonyl chromium is octahedral. Okay, so Mn2CO10 it is having two square pyramidal MnCO5 units and Mn bond is there. Okay, octacarbonyl dicobalt also has a CO-CO bridge bonding is there by the CO group. So these are the different structures that we see in the metal carbonyls. So metal carbonyls की हमें bonding देखनी है सिर्फ. So metal carbonyls they both have sigma and pi character. Okay, what happens is मेटल कार्बन बॉन्ड जो बनता है यहाँ पर, सी मेटल कार्बोनिल्स में क्या है, देयर इज अ मेटल एंड कार्बन bond. So metal carbon bond is a sigma bond. How it is formed, you know, carbonyl is a ligand. So donation of lone pair of electrons on a carbonyl carbon into vacant orbital of metal. तो जो carbonyl का carbon है, it has lone pair of electrons with it, it's a ligand. So it will donate its electron to the empty d orbitals of the metal. Okay, empty d orbital of metal. तो कार्बोनिल कार्बन इसको अपने इलेक्ट्रॉन्स डोनेट कर रहा है, सो दैट फॉर्म्स अ सिग्मा बॉन्ड. ओके, जैसे और लिगेंड्स के केस में होता है. सो दिस इज द मेटल कार्बन सिग्मा बॉन्ड. ओके, अब मेटल कार्बन पाई बॉन्ड क्या करेगा? यस, अब empty d orbitals में इलेक्ट्रॉन आ रहा है, but you know that the metal might be having some filled d orbitals also, right? filled d orbitals भी तो होते हैं ना, we have d1 d2 d3, तो जितने empty हैं there are some filled d orbitals also. So what happens is that a pair of electrons might be donated from the filled metal d orbital to the vacant anti-bonding orbital of carbon monoxide. So you know anti-bonding and bonding, we have studied molecular orbital theory. तो एक anti-bonding molecular orbital जो है आपका carbon monoxide का, उसमें electrons आते हैं from the filled d orbital of metal. So we will be calling it as pi back bonding. So this is pi back bonding. Pi bond is formed and this is back bonding, right, from metal to the ligand. So that's why we will be calling it as pi back bonding. So this is another type of bonding, a special type of bonding that is seen in the metal carbonyls that we are studying. So we call it as a synergic bond. Okay, synergic bond है and it strengthens the bond between the carbonyl group, CO group and the metal. So bond जो ऐसे strong हो जाता है because pi back bonding is also present. So you just need to remember this thing. Okay, sigma bonding कहाँ से कहाँ हो रही है and pi bonding कहाँ से कहाँ हो रही है. Okay. And lastly, applications of coordination compounds. So coordination compounds are used in various areas So they are used in analytical chemistry, metallurgy, biological system, industry, and medicines. Let's see here. So coordination compounds are used in qualitative and quantitative chemical analysis. Okay, how the familiar color reactions given by metal ions with the number of ligands as a result of coordination entities form basis of their detection. So what happens is when we are detecting what metal ion is present in this complex, okay, so we actually form some coordination entities, and based on the color that is being obtained, okay, colored reactions we get. So based on the color we get to know about the particular metal ion. Okay, like we have EDTA, dimethyl glyoxime, naphthol, cupron. So these are coloring reagents. So यहाँ पर जब हम ये डालते हैं we get different colors and we get to know about the metal ion. Hardness of water is also estimated by this complex of EDTA with sodium ions. Okay, so calcium and magnesium ions form stable complexes with EDTA, and the estimation of these ions can be done. Okay, so sodium ions can be replaced by calcium and magnesium ions, and vice versa, and we can get to know about the hardness of water. Okay, in extraction processes like silver and gold, we actually make complexes. Okay, for example, in the case of gold, it combines with cyanide in the presence of oxygen and water to form this coordination entity. Okay, and gold can be separated in metallic form from this solution by adding zinc. So these examples that are given to you na, in examples के ऊपर ही you can be asked questions on your NEET examination. So read these examples carefully. We have all taken all the examples that are given in NCERT. Okay, next is, if we want to purify the metals, it can be achieved through formation and decomposition of the coordination compounds. Like impure nickel is converted to tetracarbonyl nickel and then it is decomposed to give pure nickel. Okay, so purification हम कर सकते हैं. In biological system also they are of great importance. So you know that in chlorophyll we have this thing. It is actually a coordination compound of magnesium only, your chlorophyll. Hemoglobin that we have in our blood, it's a red colored pigment, so which is your oxygen carrier. It is a coordination compound of iron. Vitamin B12, which is called cyanocobalamin, the anti-pernicious anemia factor, it is also a coordination compound of cobalt. So you can find coordination compounds in many cases. Okay, so we have enzymes also like carboxypeptidase, carbonic anhydrase, which are also coordinated with the metal ions. Okay, now again coordination compounds are used as catalyst. Okay, for industrial processes rhodium के catalyst use होते हैं. So rhodium catalyst, which is known as the Wilkinson catalyst, it is used for hydrogenation of alkenes. ये हम organic chemistry में भी देखेंगे. Okay, next is articles can be electroplated with silver and gold more smoothly and evenly from the solution of their coordination complexes rather than from simple metal ion solution. Okay, in black and white photography, the developed film is fixed by washing with hypo solution, which dissolves the uncomposed silver bromide to form a complex ion. Okay, and in like medicinal chemistry there's a use of chelate therapy we use. Okay, example is the treatment of problems caused by presence of metals in toxic proportions in an animal and plant system. So अगर हमें वो metals remove करने हैं, okay, like excess of copper and iron, so they are removed by chelating ligands penicillamine and desferrioxime B via the formation of coordination compound. So coordination compound बना लेगी metal ion के साथ जाके, and that can be removed from the body. EDTA is used in lead poisoning. So EDTA भी एक chelating ligand है, it will form a complex with lead and it can be removed from the body. Coordination compounds of platinum, they inhibit the growth of tumors, right? Cisplatin and other related compounds are there. So these are some uses of your carbonyl coordination compounds that you have to remember. And with that we have covered all the topics of coordination compounds. Okay students, crystal field theory is also important. So try to revise all these topics. I told you to go through NCRT. Whatever questions, in-text questions are given in NCRT, please go through them, because sometimes you find questions from there also directly asked in the NEET examination. Okay. So once you do it, then you go to the MEMONEET app and there solve the line by line NCRT questions. Okay. And then go through the PYQs. This is how you approach the chapter. We'll meet in the next lecture. So until then, thank you.